Good morning, guys. Sir Dewey here again. So today we're going to discuss frame analysis on the basis of lateral loads using a slope deflection concept. But this time I'm going to use MathCAD as a tool to facilitate the computation for our simple frame here. So we have a two-story, one-bay frame loaded laterally with 10K and 20K loads at the joints C and B respectively. So before we proceed with the analysis, let's take note of the things we need to take note on as far as the slope deflection procedure is concerned. So we have here your EIS constant to simplify things. I'd like to show you how the concept slope deflection works. No? So these are the two things we need to remember, that in every member, whether it's a beam or a column, we only consider the moment, okay? Considering, let's say here, your near end of the joint and the far end of the joint here as I and J. Okay, so this I and J is a general subscript used on matrix analysis, especially when you are doing some programs. Now, to represent the nodal description, A, B, C, D, E, F, or a number description can also be used, 1, 2, 3, 4, 5, 6. Okay, so the slope deflection method works by considering the moment, let's say at the near end. Let's say this is the moment at near I, far J end consideration, and the contribution of the rotation. Okay, so we have here now your rotational behavior versus the translational behavior. So we have to bear in mind that the moment consideration or the flexural considerations always reckoned on the rotational, okay, rotational freedom of your joints and the translational freedom of your joints, such that without doing the derivation, we can simply state that the moment, okay, of a certain joint or a certain member ij, okay, so we're referring now here your near end I going to the far end j, is simply equivalent to this constant, okay, 2ek, where k is simply the stiffness that we normally consider as the ratio between your moment of inertia all over the length. Okay, so this is simply a 2ei over L multiplied by this expression here, which simply states that the effect or the contribution of the rotational, okay, the rotational degree of freedom at joint I is actually 2 times the angle theta I, while the contribution of the far end is only 1/2 of the contribution of the near end rotation. So this is simply 2 theta I plus theta j minus, okay, a contribution of the translational effect, which is simply the delta effect. Okay, this is not only true for columns, it might as well be true to beams when there are some, let's say, settlements on the support wherein joint E will be and joint D will be affected, as well as joint B and joint C. Okay, So this does not necessarily refer only to column translational displacement, but also on beam translational displacement. Okay, so the effect of this is simply an angle or the slope, which is equivalent to the ratio of your delta over L, which in this case is simply represented by the letter psi. Okay, so why is it it's a negative contribution? Because we take note that the slopes here, if we assume this a counterclockwise rotation as positive, no? So our rotation here is actually a positive rotation. Okay, it's a counterclockwise positive rotation, which represents a slope, okay, coming from the near end to the far end, sloping upward. Okay, so the slope here is upward, but it's on the positive side. This is downward, but it's on the negative side. So it's still a positive contribution. While this, okay, displacement here will induce a reverse slope here. So the slope here is actually like going here in this direction. Okay, and the slope here is going in this direction. So it must be a negative contribution here. So you just remember the 2 plus 1 minus 3, where theta I and theta j are the rotational description of the near and the far ends, while psi is simply the displacement, which is the same, no? It's a relative displacement, which represent more or less the same value or the same effect on the moment. Okay, so this is a general slope deflection equation. You can find this in different form, but they still mean the same. So I'd like you to go through the basic concept on how it was derived. But basically, this video is to go along with the procedure in the slope deflection using a MathCAD program to facilitate our computation. Of course, E, K, and theta's size are the ones described here below. So to simplify things, we can see that the length of the columns and the beams are just the same, and EI is a constant. Therefore, EI over L is simply a constant, which makes 2EK simply a constant equivalent to 1. So if we are going to relate, okay, relate the effect of the distribution of your moments brought about by the applied loads, we can simply use the relative, okay? We can simply use the relative values of your 2EK such that this can be represented by a unit, okay, or equivalent to 1, such that this expression inside the parentheses is the ones that gives importance to your slope deflection solution. So in case the properties are not constant, you just make use of a ratio, a relative ratio, to represent a factor to be multiplied per moment, okay? Moment representation, let's say Mij. So to begin with our equations, we simply again look into this general equation and remember that this is simply a 2 theta near end plus theta far end minus 3 times the slope, okay, represented by your translational displacement. Okay, so it's simply 2 theta I plus theta j minus 3 times psi. Okay, so you just remember those three things, and systematically you can get along with the moment equations very accurately. Okay, so this is now AB, so this is a 2 theta A, okay, plus theta B minus 3 of psi 1. So if I'm referring here theta member AB here, we know that there's no rotation here such that your theta at the support will simply become 0. Okay, Likewise with your theta at F. Okay, so that's why there's a zero value here. And your theta B is the contribution of the far end of your AB member, which is half of the near end. And then minus 3 psi 1. Take note that there will be translation later here, which will represent your psi 1. Okay, a chord. This is actually a chord rotation. Okay, so a chord means a connection between the two end joints, two ends, okay, that represent, okay, the slope of this deformed geometry. Okay, so this is simply delta over L, but we use psi 1 to represent the psi of this 2. Okay, so we now make use of a chord representation, which will represent your psi 1 here, which are the same, and psi 2 here. Okay, so this will now be your psi 2. Okay, again, I told you to just to look at the near and the far end. So near is B, so it must be 2 theta B plus again 0, theta E is 0 minus 3 psi 1, because you are referring to the ground story here, okay? And then BC, you have a 2 theta B plus theta C minus psi 2, because BC is on the second story, okay? And BE, yeah, this is a beam, no? The beam, since this is a laterally loaded frame, so there are no chord there are slight chord end rotation, but this chord here will not actually uh, considerably be displaced vertically because there's no load applied on top of it. Of course, the self weight may induce, but we neglect the effect of the self weight. Okay, so this is 0. And then CB is 2 theta C plus theta B minus 3 psi 2, again on the second floor. And then CD is 2 theta C plus theta D plus 0, because this is a beam. So all of these zeros here refer to your beam. Okay, your beam member. And all those who have the psi 1s and the psi 2s are your column member. Okay, so you just follow 2 theta D, theta C plus 0, 2 theta D plus theta E is just 2, 1. Okay, 2, 1. So where's the 2 coming from? The first letter of your subscript here. Okay, so 2 theta E, theta D minus, okay, these are all negatives, okay, etc. So without really looking back to the equation, you can actually formulate it, but just be cautious on the size, the psi value, because you need to refer the psi value on each floor, okay, when you're considering column translations. So satisfying the equilibrium of moments of the joints, we simply take the summation of moment at joint P equals 0. So you just take all the moments at this joint, BA, BE, and BZ equals 0, as well as joint C, we have the CBCD equals 0. At joint D, we have the DCD equals 0. At joint E, we have the EFEBED equals 0, etc. Okay, so we can now formulate simply plugging it in. So this is the good thing about a program. So you just plug in the values. You can actually simplify it into this equation, etc. Okay, joint C, it's MCB, MCD. Joint D is MDC, MDE, etc. So you will actually make 4 equations out of this summation of moments at the joint, and additional 2 equations can be obtained from the satisfaction of equilibrium of the horizontal forces at each story level by simply summing up the story shear forces. So the story shear force at at the second floor is simply VC plus VD plus 10 equals 0. Okay, so this is just the VC here. We have the shear here, okay, and the shear there. So we have a VC plus VD, okay? Okay, of course, this is a reactive force. We are talking now here of the summation of the force per each story. So these are all positives. Okay, so this is again your V D at the second story. Sorry, ground story, which is equivalent to the shear. You have to add this to be 30K to be carried by the shear at the second, the ground story, because the ground story carries both your floor, second floor, and the third floor here. Okay, so we have an equation now in this form, and also you have an equation in this form. And again, you need to just plug in all the moment equations you have derived here. Automatically, the MathCAD gives you a way of making things simpler. But of course, if you don't have any tool, you have to just be patient in dealing with the values of the moments in terms of the rotation and the translation. Okay, so the division of 20 here is simply means you divide the moment with the length in order for you to get the shear values. And everything now will be obtained by simplification. At the second story, you have this as your equation 5. The first story, you have this as your equation 6. And simplifying things out, summarizing all the slope deflection equations from 1 to 6, we have actually 6 equations with 6 unknowns. We do the computation in a matrix form. So we now assemble the matrix, which is actually the stiffness matrix, the flexural stiffness matrix, equivalent to this one. Okay, so 6, 1, 1, minus 3, minus 3. Okay, there's a 0 here because we have no theta d here. Theta d equals 0, so it must be consistent. B, C, D, E, psi 1, psi 2. Okay, so that's why there's a 0 here. Okay, there's a 1 for 1 and then a 0 on the E, 0 on the psi 1, and negative 3, and so on and so forth. You just write this down one by one into the matrix. This is a matrix of coefficient which represent your structure stiffness matrix in flexure. Okay, similar to the stiffness equation K, if you are doing a systematic stiffness procedure, finite element procedure. Okay, and then you multiply it by the generalized displacements, which starts from theta b, theta c, theta e, minus, psi 1 and psi 2. Don't mind the sign there because the signs will be carried by the matrix coefficients. Okay, and then equate it to your value of constants, which becomes negative when you put it on the other side. So this becomes negative 200 and negative 600 using a MathCAD inversion. Okay, and multiplication, you get this as your displacement. So these are now the generalized displacement, meaning to say these are actually corresponding to the degree of freedom at the joint, which represents your theta at the B joint, the rotation theta at the C joint, the rotation theta at the D joint, the rotation theta at the E joint, and your chord rotation at the ground floor and the chord rotation at the second floor. Of course, theta A and theta F are known to be 0 because there are no rotations, so you just fix them here in order for you to get the value of your member end moments. So the member end moments gives you now your member stiffness matrix, which is this one here. So where did I get this local stiffness matrix? So this is the small letter K, this is the member stiffness matrix, which is actually coming, okay, from moment equation. Okay, so this is the local. So you just go back to this moment equation. You are now referring here always on the AB, this must be a theta A, theta B. Okay, theta A, theta B, psi 1. Because this is a column, there is a psi 1 here. So the beams has no size, so 0 automatically. Okay, so I just get it from MAB and MBA. So this is now a 0, 1, negative 3, and a 2, 0, negative 3, which I just transformed into a matrix equation for me to handle it very fast and very accurately. Okay, 0, 1, negative 3, and 0, 2, negative 3. Theta A, theta B, psi 1. Theta B, theta C, psi 2. All the columns have size, and all the beams have 0 as their size, psi value. And automatically, this will be your moment at the member ends, okay, which happens to be symmetrical in some uh, values, okay. So for the sign convention, just take note that a negative sign here indicates a counterclockwise moment, okay. Counterclockwise moment is a negative sign. Okay, so a clockwise moment is a positive sign. Okay, so if I plot the sign here of if you remember AB, so this is now a negative 176, so it must be a counterclockwise moment like this. Okay, so this is actually behaving in this manner. So for the beams, okay, for the beams, let's say member BE is a beam. How do I know that this is a beam? Because there's a 0 chord rotation there. So this is a 158. Therefore, my beam member is a clockwise member. So my end rotation is like this. Okay, so this is a positive value, it's a negative value. So this refers to these moments here, and this refers to these moments there. And so it's true with this because these are both negative. So you can now draw and plot the end moments in the frame uh, for ease of reference. So that's how slope deflection works using a MathCAD tool for a laterally unbraced frame. Thank you very much for listening. So have a nice day. I'll see you in the next video.